Hello, all. I want to welcome you to today's class. Today, we'll be looking at Lewis structure of molecules. Remember, in this chapter, we've been talking about different types of bonds, and we talked about ionic compounds. And we started talking about covalent molecules. We've looked at how to name them, and today we'll be taking that one step further by knowing what their structures looks like, and that's exactly what we're going to be doing today with the concept of Lewis structure. First things first, I have a beautiful quote here. I'm not going to talk about it. I'm just going to read it. It says, opportunities are usually disguised as hard work, so most people don't recognize them. This quote is from Anne Landers, and something you can think over about, and is a food for the soul. And let us take it immediately to our learning objectives. Today, we have two basic things we want to address in this lecture. First, we're going to learn how to draw correctly the Lewis structure. Draw correctly the Lewis structure. The Lewis structure is seen as the two-dimensional structure of covalent molecules. We're going to know how to do this. And then secondly, we're going to understand what is resonance, and then we'll draw Lewis structure of compounds that exist, simple resonance structures. All right, let's take it off from there immediately. What is Lewis structure? That's the next question we ask ourselves. Lewis structure simply represents the chemical structure of covalent or molecular compounds. What does it show? It shows how atoms are arranged. Remember, the formula of a compound will tell you the number of atoms in it. Like if I write H2O, I know the number of atoms involved, which is about 3 atoms involved. I know the identity of the atoms. There are 2 atoms of hydrogen and oxygen, but I don't know how they are arranged. Now, these are those things, those nagging questions is what is being answered by the Lewis structure. So the Lewis structure shows us how these atoms are arranged. And not just that, it tells us the type of bonds that are formed. Now, these bonds can be, it can form a single bond between the atoms. It can be a double bond. The bond can also be a triple bond. So these are the things we're going to find out. And this is achieved by writing what we call the Lewis dot structure, according to the founder Jean Lewis. Now, these dots are actually represent electrons, using electrons as dots, just like we did earlier when we looked at the Lewis structure of individual atoms themselves. Now, again, the guiding principle here is that every atom must have to satisfy the octet rule. Every atom will have to satisfy the octet rule. And what it simply means, they're going to have 8 electrons in the atomic shell. And of course, we've already discussed that in the previous lectures. So basically, now let's look at this. Now, there are some important things I need to show you. Now, let me talk about generally what the Lewis structure is all about. Now, if we have the Lewis structure will be, an atom A is connected to 4 other atoms. So in this case, atom A is seen as what we call the central atom. Let me use a different color. So the atom A is seen as the central atom. And these atoms that are attached to it are seen as what we call the peripheral or attached atom, the peripheral atoms. Now, again, I said these bonds could be into 3. There could be a single bond. Now, every single bond, one single bond represents 2 electrons. So anytime you see a single bond like this, it's 2 electrons. Now, 2 single bonds, or say double bonds, or you say double bond, 2 bonds, or you can say double bond. Every double bond represents, of course, it's going to represent 4 electrons. So if you have an atom that has 2 bonds with it, it is 4 electrons. And then 3 bonds, or what we call triple bonds, every triple bond will represent, of course, 6 electrons. So we can say this is a pair of bond. A pair of electron is a single bond. Now, a double bond simply means two pairs of electron, which is 4 electrons. And the triple bond simply means 3 pairs of electrons, which is 6 electrons. And of course, each of these guys represent, again, I'm going to write this. This is important. We get this foundation. This simply means 2 electrons. This again means 2 electrons. This again means 2 electrons here. And this again means 2 electrons. So basically, if you look at this atom A, it is surrounded by 8 electrons around it. And every atom, apart from hydrogen, has to be surrounded by 8 electrons in its outermost shell. Now let's take it on from there. Now, what are the steps we're going to use in writing the Lewis structure of these molecules? Now, the steps are here. I want you to read this up yourself and try to make a meaning around it. But I'm going to really go over it through very fast. And then as we practice, we're going to figure them out. The first thing we need to do is to determine the valence shell electrons present in that compound. How do we do this? We know that each of these elements have their individual valence shell. You get that valence shell and add them together to determine the total valence shell of electrons in that covalent molecule. 2. Now, if it is a cation, at times we counter cations. A cation means an element that has lost an electron. What it simply means is that we're going to remove the equivalent number of electrons that correspond to the number of positive charge. And then, if it is an anion, we're going to add the number of what? We're going to add the number of electrons that corresponds to what? That particular charge on the anion. So for the cation, you add. For the anion, for the cation, you remove, for an anion, you add. And 2, what else do we do in step 2? We're going to surround we're going to identify a central atom. Remember what I said earlier? The central atom is important. You figure it out at this point. A central atom is an atom that is surrounded by at least 2 atoms. So this, you have to determine the central atom. And the central atom is usually the least electronegative atom. Least electronegative atom. That's usually the central atom. And then what else do you do? We have to attach the peripheral atom. The peripheral atoms are those atoms that are attached to the central atom. And then we have to first of all make sure that the peripheral atoms satisfy the octet rule by sharing the electrons around them. Now, I usually tell my students, if you're drawing the Lewis structure, you are an electron manager, managing the number of electrons. So you have to make sure that these electrons are evenly distributed between first the central atoms. And if you have any remainder, you cannot take it back to the central atom. And lastly, if the atoms do not have enough pairs of electrons, what do? You can move them around and use them to form double or triple bonds. Let's put this into practice. Of course, let's put this into practice. That is the best way to figure it out. And before we do that, there are tips, important tips that you need to know. These tips help students a lot. Hydrogen can never be a central atom, never. Carbon, anytime you see carbon, carbon is almost always the central atom. And then the central atom is usually atoms that are less electronegative. I just said this in the previous page. And finally, remember that every atom must satisfy the octet rule. There could be instances where it doesn't satisfy, but at the level of this GOB series, we're going to concentrate that on those atoms that have to satisfy the octet rule. And those are these. Now let's go into our problem. Problem 1. First of all, we have to practice on how to calculate the number of electrons in the valence shell of these atoms. So that's what we're going to do first. Now, what do you do again? Remember again, how do we know the number of atoms or the number of electrons in each atom? That has to be done by knowing the group. So let's look at this. This is methane, CH4. Carbon is in group 4. Every group 4 element will have 4 electrons in the outermost shell. So that's what we know. Group 1, hydrogen in group 1 will have what? 1 electrons in the outermost shell. So what do? We go straight to this. Carbon is 4, we put 4 plus. Hydrogen has 1 electron in the outermost shell, but there are 4 atoms. So what it simply means is that we're going to multiply 4 times 1 electron. If you add all this together, it's going to give you 8 valence electrons. So you have total of 8 valence electrons in this compound. Let's go to H2O, which is water. Hydrogen again will have 1 electron, and there are 2 atoms. So we're going to say 2 times 1 plus. Oxygen is in group what? Group 6. Remember, group 6 guys will have 6 electrons. So what it means, we're going to add is 6. And if you add that, it's going to give you 2 times 1 is 2. 2 plus 6 will give you 8 valence electron. Again, let's go to this one. Now, this is a good example of an anion because it is negatively charged. Sulfur, again, is in group 6 here. So sulfur is in group 6 to have what? 6 electrons. We add it plus. Oxygen is in group 6 again. Look at oxygen here. But it has 4 atoms. We're going to say 4 times 6. That's 4 oxygen atoms times 6 electrons. And then look at this. This is 2 minus. Remember we said in the rule, if you have negative charge, you have to add equal to the magnitude of that charge. So what are we going to do? Since this is negative and that is 2, we're going to say plus 2. And when you do 4 times 6, will give you 24. 24 plus 6 will give you 30. 30 plus 2 will give you 32 valence electron. This is what we have in SO4 2 minus. So I want you to pause this video quickly and then try to do these problems yourself. And then you can unpause it and see how much you have done. Again, let me take it off from here. PO4 3 minus. P is phosphorus. Phosphorus is in group 5A, and they have to have 5 electrons in their atmosphere. So it's going to be 5 plus. Oxygen is in group 6 again. Remember that? It's in group 6, you have 6 electrons. So it's going to be, and there are 4 atoms. 4 times 6. And then there are 3 minus. 3 minus simply means we're going to add plus 3 to this. And when you add everything together here, it's going to give you 32 valence electrons. Again, look at ammonia, ammonium ion. Here it is positively charged, 1. Now this is nitrogen in group 5 again. So we're going to say 5 plus. Hydrogen is in group 1, 1 electron. So we're going to say, and there are 4 atoms, say 4 times 1 electron. This is plus means plus 1. So what simply means, since it is plus 1 charge, we're going to do what? We're going to remove minus 1. So this 4 times 1 is 4. 4 plus 5 is 9. 9 minus 1 gives us 8 valence electrons. We take it up to the next one. CH2O. Again, carbon is in group 4. Group 4 will have 4 electrons. There are 4 plus. Hydrogen is in group 1 again. We said it already. It's going to be 2 times 1 electron plus. Oxygen is in group 6 plus 6. So if you add all this together, this is going to give you what? 2 plus 6. 2 times 1 is 2. 2 plus 4 is 6. 6 plus 6 will give you 12 valence electrons. So this is how you do these problems. Let's move really quickly in drawing the Lewis structures. Let's start with drawing the Lewis structures of very simple. We say draw the Lewis structure of O2. Remember the rule. The first thing we need to do is to calculate the number of valence electrons in this molecule. This is a molecule of oxygen. There are 2 atoms of oxygen, and oxygen is in group 6. It's in group 6. So it's going to have 6 electrons. So we're going to say 2 atoms times 6 will actually give us 12 valence electrons. So we have 12 electrons to share between these 2 atoms. Now, since this is just, it only has 2 atoms, you can choose any one of them to be the central atom. So what do? I'm going to just write O and attach it to another O because there are only 2 atoms here. So I can choose any of them. So I'm going to choose this one as my central atom. That means I have to satisfy this one first. Remember, I have 12 electrons to go, but I've only used 1. So I'm going to add here. I'm going to try to add it here. So I'm going to say, I'm going to add this one. Now, remember again, a single bond. I'm using single bond here to represent 2 electrons. All right? And remember, those electrons that are not actual, those electrons that are not used to form bonds, we call them the lone pairs of electrons. Although we're going to talk about this in the next chapter when we look at molecular shapes or molecular geometry. So now let's see. We've used how many electrons? Let's count. So this is 2, 4, 6, 8. We still have about 4 electrons. So we can go here and start satisfying 8. So we can say 10 and 12. Okay, wait, I'm going to like to do it this way. Okay, we can say 10 and 12. Now, so let's count again. 2, 4, 6, 8, 10, 12. We've used all of our electrons, but what else do we do? Is this correct? How do we know if it's correct? Each atom has to satisfy the octet rule. Let's count. This atom has 2, 4, 6, 8 satisfied. This one has 2, 4, 6. Oxygen wants to have 8 electrons. Here it has 6. What are you going to do? We start being even-handed. This is the place you start being even-handed. What do? I'm going to remove this one lone pair here and share the bond between the two of them, just to be even-handed. So what do? I'm going to take away this bond. Look at what I'm going to do. I'm going to take away this bond now. I'm going to bring it in between these two. So that's what I'm going to do. So I'm going to bring it here. And what it means is that I'm going to clean it. So to clean this away, I have to erase it. So you need to know that this involves trial and error, and that is the best way to figure it out. And again, let me count. If we count again, what do we have? If we count this one again, we now have 1, 2, no, sorry, we have 2, 4, 6, 8, 10, 12. Every one of them is satisfied and still have within the limit of our 12 electron. So if you want to count the number of octet through, this oxygen has 2, 4, 6, 8. This one has 2, 4, 6, 8, and both of them are satisfied. And therefore, this becomes the legitimate Lewis structure of this compound. Now, let's do that of HCN. HCN, again, we have to calculate the total valence electron. Again, let's do it. So it's going to be, hydrogen is in group 1. We're going to have 1 plus is in group 1 here. Remember, don't forget that, 1 electron. Group 4, this is group 4. They're going to have 4 electrons. So 1 plus 4, and nitrogen is in group 5. These guys are going to have 5 electrons. So it's going to 1 plus 4 plus 5. If we add everything together, you're going to have 10 valence electrons. And now, remember what I told you in the tips I gave you? That tips help. I told you carbon is always the central atom. That comes in mind very fast. So we're going to say carbon is the central atom. We're going to attach the other two to it. Now, we have 10 electrons to distribute between these atoms, but we have only used what? We've only used what? We've only used 2, 4. So we have 6 to go. However, what did I tell you in the tips? In one of the tips, hydrogen can never accept more than 2 electrons. So whenever you put a single bond, it is satisfied. And it can never be a central atom. So what that thing means, we have to deal with carbon and nitrogen that is supposed to have up to 8. Here, carbon has 2. Nitrogen has what? 1, 2. Carbon has 2, 4. Nitrogen has only 2. So let's satisfy the nitrogen first. Now, from this, the remaining of these 6 electrons, we're going to satisfy these guys. So it's going to be 2, 4, 6. So if you count 2, 4, 6, 8, 10, we've used all our electrons. But what do you see there? You look at this. Carbon only has 2, 4. It's not satisfied, like we did before. We're going to start removing. So I'm going to remove an electron from here. I'm going to remove this one and use it to form a double bond here. If you look at that, it is not still satisfied. Carbon is done because 2, 4, 6. It wants one more. What am I going to do next? I'm going to remove one more. So I'm going to remove one more here and use it again to form another bond. So I need to have a good triple. So I'm going to clean that and make it to look cleaner. The 3 bonds look very clean. So it's going to be this and this. So this becomes the true Lewis structure of HCN, whereby carbon has triple bond to nitrogen and a lone pair on nitrogen, whereas carbon has only 1 double bond to hydrogen. This is the legit Lewis structure of this molecule. So you can pause the video as always and try to practice this problem and always come back to them. Let's do these problems now. Now, to draw the Lewis, remember the Lewis structure is the 2D of molecules. Don't forget, it's the 2-dimensional representation. Because after this, the knowledge of this will be applied in knowing what is the 3-dimensional structure of these molecules. Okay, again, let's calculate the valence electrons. Nitrogen is in group 5 as usual. It's going to have 5 electrons. So it's going to be 5 plus. Bromine is in group 7. So it's going to have 7 electrons. And there are 3 atoms. So we're going to say 3 times 7. 3 times 7 is 21. 21 plus 5 will give us 26 valence electrons. Now, if you look at this, this is easy for you to figure out. If you look at between this now, anytime you have a single atom and other ones around it, that tells you that atom is likely the what? That atom will likely be what? Will likely be the central atom. So that's exactly what we're going to do here. So let's do that. So it's going to be N. Again, it's going to be N. And then we're going to, since we have 3 things, so let's try to, usually I tell students, try to distribute this as if you just have 3 things around it. So we have 26 electrons, we've only used 6, we have 20 to go. So what do we do next? We have to satisfy the peripheral atoms. I'm going to start giving 2 electrons to each of these guys. So this 2, 4, 6, 2, 4, 6, 2, 4, 6. So we have 26 electrons. Let's know how much we've distributed so far. So I have 2468, 2468, 2468. So I've distributed 8 times 3 is 24. But I have 26. Now, 1 is remaining. What do I do? Where am I going to put that one? Since all the peripheral atoms are all satisfied, the remaining atom should go to the central atom. And where do I put it? I'm going to put it here now. And this becomes the legit Lewis structure of this molecule. Let's get to the next one. Ammonium ion. Remember, we calculated the valence, we calculated the distance for this molecule earlier. So what do we do? Again, this is group 5. Nitrogen is in group 5, is 5 plus. Hydrogen is in group 1, 1 electron, and there are 4 atoms. And then plus means we're going to do what? We're going to just remove 1. So the 4 times 1 is 4 plus 5, 9, 9 minus 1 give you 8 valence electron. Again, nitrogen will be at the central atom. Remember, hydrogen will never be. Don't forget that. What's the next thing we do? There are 4 things attached, 4 hydrogen atoms. We try to put that around it. Now, if you do that, let's count how many electrons we have. We have 2, 4, 6, 8. We've used 8 electrons already, and we have 8, and that is it. Because this makes sense. Nitrogen already has 8 electrons. Hydrogen has only 2, because it can't go beyond that. This remains the Lewis structure of this molecule. However, you have to show that this sign, because this is a charged entity, it's a charged ion. You have to say where that charge is. How do you do that? You put a square bracket around it and then put the charge. Either it is positive or negative, you have to indicate that, and this is very, very important. If you don't do this, you are bound to lose some point in exam, and you have to always do it every time. Again, we're going to keep drawing more structures as more examples. So draw the Lewis structure of the following. Again, the first thing first, we have to calculate the total valence electron. So you can always pause this video, try out these problems yourself, and always come back to them. So hydrogen has 2 atoms. Hydrogen is in group 1. I've been saying this all the time now, so by this time you should be memorizing those. So this is 2 times 1 plus oxygen is in group 6. You have 6 electrons. So it's going to be, and there are 2 atoms, 2 times 6. So this is going to be 2 times 1 is 2. 2 plus 12. That's going to give us 14 valence electrons. Now, you will now draw. In this kind of, remember, in this kind of problem, hydrogen is always going to be, cannot have more than 2 electrons. This kind of problem can be deceitful. You usually have 2 atoms that looks to be the central atom. So look at how you're going to draw this. Your hydrogen is going to always be, if you don't draw this way, any other way you're going to draw it, you're going to struggle to do that. So because this kind of atom usually have 2 central atoms, and we're going to see that in drawing the 3D structure, we just choose 1 conveniently and the central atom. So we have 14 electrons, and we've used 2, 4, 6. We still have about 8 to go. So what do? Hydrogen is satisfied, so we need to deal with what? Our oxygen. This oxygen has 2, so that means it has to accept another 2. So it has 4 electrons, so this 2, 4, 6, 8 is satisfied. We have to add another 2 here. And when we count totally, we find that we have 2, 4, 6, 8, 10, 12, 14. Our electrons is complete, and everybody is satisfied, and this becomes the Lewis structure of this molecule. Let's go to the next one, OF2. In OF2, what do we have there? In OF2, what do you see? You see that we have 1 atom of oxygen. Oxygen is in group 6, plus fluorine is in group 7. Remember again, group 7 we have 7 electrons, 6 we have 6 electrons. So, and there are 2 atoms, 2 times 7. 2 times 7 is 14. 14 plus 6 will give us 20 valence electron. Now, in this kind of compound, whenever you see an atom more than 1, you know that would likely be the peripheral atoms. So here oxygen is going to be at the center, and it makes sense because here oxygen is less than negative than fluorine. So we're going to have F on both sides attached. Now, right. Okay. Now look at that. If you look at this, we have 20 electrons. We've only used what? We've only used 4. However, you need to satisfy the peripheral atoms. Let's satisfy them. So this is going to take extra 3 lone pairs. This is going to take another 3 lone pairs. So this becomes 8 plus 8, 16. We still have 2 to go. because there are 20, we have used 16. So we're going to now put it on oxygen. And if you put on oxygen, oxygen now has 2, 4, 6, 8 is satisfied. And this is the Lewis structure of OF2 minus. Now we continue doing our problems. Now remember, in most of my lectures, I usually do a lot of problems because I believe in doing more problems and practicing. That is the only way you get perfect, because I remember a British saying that says practice makes perfect. Now for this type of molecule, again, remember what I told you. Carbon will always be the central atom. So in this case, let's calculate the total valence electron. So it's going to be 4 plus 3. Carbon is in group 4. You can always look at, I didn't put the periodic table here, but you can always look at the other ones I have here. Group 4, hydrogen in group 1, but it has 3 atoms plus. Oxygen is in group 6, 6 electron plus. There's another hydrogen 1. If you add everything here, you're going to have 14 valence electron. Again, carbon will always be a central atom. And then we have to surround. Look at how this is drawn. Looks like this carbon is around 3 hydrogen. That can help your times. And then you want to connect it to oxygen and then to hydrogen. Now if you, let's count how many electrons we've used. 2, 4, 6, 8, 10. We still have 2. And that makes sense because this is not satisfied. You still have 4 electrons. So we're going to make this nitrogen, this oxygen satisfied. And this is our Lewis structure of, actually this is called methanol or methyl alcohol. The same thing goes for this one. In fact, these 2 compounds are organic compounds. And most of you that will be going to part 2 of this class, you're going to be seeing a lot of these things. So that is why it is good I started introducing it for you again. And I want to give you a good hint of doing this. Try to write these Lewis structures the way the formula is written. If you look at this now, carbon has 3 hydrogens here. This carbon, again, will have an oxygen and an OH group. An OH group is actually called a methanol, an alcohol group. It's an alcohol group. So this is actually an organic acid. Let's see how that is drawn. So let's calculate it. Here we have carbon is 2, so let's just say 2 times 4 carbons plus hydrogen is 3 plus 1 here is 4. So let's say 4 times 1. I didn't do it here, but it's okay. You can do it individually if you want. Plus oxygen is 2. There are two oxygens here. If you add everything together, it's going to give you 24 valence electrons. Again, I'm going to write my carbon connected to 3 hydrogen first, and then there's another carbon here connected to oxygen and connected to another OH. This is what the skeletal structure might look like. But we have 24 electrons. Let's see. We have 2, 4, 24 electrons. We've used how many? 2, 4, 6, 8, 10, 12, 14. We're not done. So now we still need to make sure that every molecule here is satisfied. So let's satisfy this. If you satisfy this, this is satisfied. So it forms 2, 4, 6, 8, 10, 12, 14, 16, 18. 18, we're not done. If we say 18, 20, 22, and 24, we've used all our electrons. But look at this. This is wrong. This carbon is not satisfied. So therefore, we cannot be using this. What do? We need to make this carbon satisfied because this carbon have only 6 electrons around it, 2, 4, 6. So what do? We're going to clean out one of these electrons at this point and use it to form a double bond between carbon and this. And if you look at it now, carbon has 2, 4, 6, 8 electrons, and the carbon is satisfied, and all oxygen is satisfied, and this becomes the Lewis structure of this. This molecule is actually called ethanoic acid, or as old name is acetic acid, and you're going to see more of these in the lab. So this is how we draw the Lewis structure. Now let's try to deal with the last objective of this lecture, is how to draw resonance structures. Now, what is resonance? Resonance structure simply means that a particular Lewis structure can be drawn. Let me put it this way. More than one Lewis structure can be drawn for a particular compound. What it means is that a compound can have 1, 2, 3, 4, 5, 6, 7, 8, and more Lewis structures. And when that scenario is possible, we say that that compound exhibits resonance structure. And the reason why resonance structure actually occurs is because bonds or electrons can move about between these atoms. And in fact, those resonance structures are not different from the other. They are the same thing. So we take them as what? As the average of all those structures. That is actually how we do them. So let's start by drawing this one. Now, nitrate ion is NO minus. Let's calculate the total electron it has. So nitrogen is in group 5, 5 plus. Oxygen is in group 6. So and there are 3 of them. 3 times 6. -1 means we're going to add +1. If you add this together, it's going to give you 24 valence electrons. Now, let's draw the Lewis structure. The first thing we need to do is we're going to put nitrogen at the center here, and then try to put oxygen around it. That's what we're going to do. Oxygen and oxygen. Now, we have 24 electrons. We use 6, so we have to satisfy oxygen around. So let's start. If we start from this one. I'm going to satisfy this one, and then satisfy this one, and then satisfy this one. Let's count. So we have, this is 8, 8, and 8. 8 times 4 is 24 electrons, which is, we've used all our valence electrons, but our oxygen is all satisfied with 8 electrons, but the nitrogen is not, so we have to move around something. What do? I'm going to move around. So I'm going to move around this guy. So I'm going to remove one of these and use one of those 2 electrons to form a double bond. And when you look at this, this is satisfied. This becomes the Lewis structure of this molecule. And then we have to put the square bracket as an ion as usual. Now, if you look at this structure, you find out that this structure, something can be manipulated. We can make some manipulations here to produce 2 more Lewis structures for this molecule. Why? If I decide to move this bond to this place and make this one a single bond, it's still going to be possible. I'm still going to get the same thing. So let's see. Let me do that. If I have my nitrogen here, and then remember here now, I'm going to add a single bond here. And if I move the double bond to this place, and also keep my distance to this place, what do you see? It still satisfies the octet rule completely. And I still have a complete octet rule obeyed in this structure. So this becomes the Lewis structure of this. And this also can be done again. Remember the first one, it was here, we moved it to this place. Let's move it to this last one here. So it's going to be, if we move it again, it's going to be N. Of course, this is now going to remain a single bond. This will be a single bond, and the double bond is going to be localized to this place. And you must have to include this square bracket when you are drawing various resonance structures of these molecules. So you see, these are the 3 resonance structures of this, and we're going to have a similar thing to the next one we're going to draw. For this selenium trioxide, let's see. In this case, selenium is in group 6, 6 electrons, plus oxygen is in group 6, and there are 3 of them. So 3 times 6. So if you do 3 times 6 plus 6, how many electrons do we have over there? We got 3 times 6 will give us 18, and 18 plus 6 will give you 24. So it's still going to be 24 valence electrons as well. So what are we going to do? The next thing, we're going to try to, now selenium is going to be the central atom in this case, as you see. So we're going to put selenium there. We're going to try to distribute this oxygen around it. And if you do again, like we did before, you see, if you satisfy this oxygen, look at, let's see that. What do you find out? You find out that what? This oxygen is 8 times 3 is 24. But selenium is not satisfied. So you're going to move it, you're going to move the bonds around again. So I'm going to move it. So I'm going to try to move it from, if I move it from here, what am I going to have? I'm going to put a double bond here, and this is satisfied. So this becomes the first resonance structure. What do I do next? Is to move the bonds around. So I'm going to move it from here to this one. If I move it to this one, this is selenium now. This is going to be a single bond. This is going to be the double bond. And this is going to be single bond as well. And then the last one, I'm going to move it to, it was here, I moved it here, I'm going to move it to the right. So it's going to be SE. Again, it's going to be here. I'm going to satisfy this one. This one is going to have a single bond. and this one is going to be this. So this becomes the third Lewis structure. Now remember, whether it is charged or not, Lewis structures must be represented in square bracket. Equivalent structures must be represented in square bracket. It is all these Lewis structures that is seen as an average of these of them. It doesn't mean that this molecule occurs in 3 different ways, but this particular movement is happening at the same time, and we can say it is the average of all these structures. Now we go to the last problem. So you can easily pause this video, try out this problem yourself. I'll give you a few seconds and we'll finish it, and that will be the last one. Okay, let's do it really very quickly. Now, the first thing we need to do is to calculate the valence electron. Again, carbon is in group 4. We've used it a couple of times, plus oxygen is in group 6, but we have what? 3 of it. So 3 times 6. And then this is -2. Simply means we're going to add plus 2. So if you add all this together, it's going to give you 24 valence electron. And then we start. If we start, okay, I'm going to put my square bracket to help me with the space. So I'm going to put carbon here. I'm just going to draw what it looks like immediately because I've already done this practice already. I'm just going to make it straight what it will look like. So it's going to be this. And then you're going to now begin to move the bonds around. So again, I'm going to move the bond. I'm going to put a single bond here. I'm going to move this bond to this place. And then this will also be a single bond. And lastly, I'm going to move this one, carbon. I'm going to move this one here. I'm going to have a single bond here too. And the double bond is going to go to this way. And then this will be the last resonance structure of this molecule. And when you count all these things, you find that each of them satisfies the octet rule. The last problem, but not the least, is NO2 minus. Again, we're going to have nitrogen is in group 5 is 5 plus oxygen is in group 6. It's going to be 2 times 6. And then because of this negative, we're going to add what? Plus 1. And when you add everything, it's going to give you what? 18 valence electron. And again, nitrogen is going to be the central atom because in this case, if you put your nitrogen surrounded by oxygen and by oxygen. So we have 18 that we've used to, so we satisfy this one. So this means that this is 2, 4, 6, 8. This is 2, 4, 6, 8. If you do 2, 4, 6, 8, 2, 4, 6, 8, what does that give you? So it gives you, yeah, 8 plus 8 is 16, right? So you put 1 here, it's 18. But you see, this nitrogen is not satisfied. So what we're going to do, we're going to move something. You can move anywhere. So I can move one of these here. Again, I can move this one here first. If I move it, I'm going to use it to form a double bond to make sure that nitrogen is satisfied. And this becomes the Lewis structure of this molecule. However, because this one has just 2 things attached, when there are 3 things attached, it will have more Lewis structure. This one is going to have only 2. So what it means is I can easily move this side towards this side and form another equivalent Lewis structure. And that will be, if I have my nitrogen at the center again, I have my oxygen here. If I move this double bond to this side and here, put single electrons here, this becomes the second equivalent Lewis structure of these molecules. Like I said, you can always pause this video, watch them, practice it yourself, unpause it and check it for understanding and proper comprehension. And this is where we draw the curtain close on this lecture again. Thank you for listening and do have a wonderful day. Bye.